Hello and welcome back to the lab. Today on the bench is nothing. This is going to be a question and answer video. I'm going to go in depth into a question that I have been getting repeatedly, and I promised some viewers and subscribers that I would do a deeper dive into this topic. On that note, for everybody who has joined us in the lab, thank you for being here. We've very much appreciate that. And I have been very much enjoying the discussion in the comment sections of all the videos, and it's been fantastic. So, thanks for being here and a member of the channel. I've been getting a lot of questions recently about the GPSDO, how it's hooked up, and what it's doing for me here in the lab. So this is I think I'm going to title this video 10 megahertz reference and why you want one, or why you might want one. Now, what I'm going to do in the lab, or what I'm going to do right now, is I'm going to show some pictures of what I've got pointed in several spots, and but I don't want to dig the equipment out. It's way behind the bench, and also it takes quite some time for this to stabilize. We're talking about like 2 weeks. So there will be some actual photo, or there will be some stuff on camera, and I will be doing some things. Showing some of the actual units, but for some of this stuff, I'm gonna use pictures due to inaccessibility of the devices themselves. So I would be remiss in starting this about 10 megahertz reference if I didn't start talking about this component right here. This is a crystal, and especially some of the newer crystals. They come as a package. You put 12 volts in them, depending on what they require, and they shoot out a square wave on the other end at a given frequency. That depends on the actual cut of the crystal and things like that. This particular one, if it will focus, it will probably not. Oh, yeah, there we go. Is a 6 megahertz crystal. So not 10 megahertz by any stretch of the imagination, but this is kind of what we're disciplining. Now, the problem with crystals is they vary widely, especially with temperature. The frequency can swing all over the place. This is a non-ovenized crystal. We'll get into that in a little bit. And it's also very hard to sync to free-running oscillators. It doesn't take much for them to be off of frequency, and if they're off of frequency, they will not keep phase with each other. This is some of the stuff we get into with PLLs and a few other things, phase lock loops. This can affect different pieces of equipment as well. Scopes, spectrum analyzers, function generators, frequency counters, time mark generators for different pieces of equipment, and things of that nature. One of the other problems is with stability as you multiply up. So let's say you have a base clock of 10 megahertz, but your end goal's 50 gigahertz. Any error in that 10 megahertz reference is going to get multiplied up into the higher bands. So if you have, say, 1000x multiplication off of your base clock, you will have 1000x the error multiplication as well. Phase noise, frequency, there's jitter in the clocks too, which can ultimately turn into phase noise. But so as you go up in frequency and you multiply up, it becomes a bigger and bigger and bigger problem. The other problem is expense, both in cost and power. The more accurate clocks you have, another YouTuber named, Shariard from the Signal Path, he did a video where he has so much RF gear, he was burning something like a kilowatt of standby power with his lab off. Plugged in, everything turned on, just keeping the ovens warm and everything like that. It was burning 1,000 watts of power. So he had to add power strips to some of his benches to to be able to shut some of this stuff down. That also gets into some warm-up time, which we'll get into as well with different crystals, and knowing what the warm-up time is for some of for your specific device. for instance, type 184, if I have it on and I have the oven hot, because it's got an OCXO in it, which is an ovenized crystal, it's a 30-minute warm-up. I have to turn the device on, let it wait for 30 minutes, get it warmed up, and it's ready to go. If I have it cold, where the oven hasn't been on, it's a 4.5-hour warm-up before it's meeting its specification. And the frequency likes to drift all over the place. So some of the warm-up times and things like that are very important for some of these. And typically, the more precise number of zeros, the longer it takes to stabilize. So, to get started, I had a problem in the lab, and I've gone into this in some of my other videos, but I got a TG501 and a Type 184 that I needed to test. So I needed some pretty accurate clocks. And that became a bit of a challenge. So what ended up happening is I picked up a Agilent 53131A, which is my frequency counter. I will leave a link. There will be a lot of links in the description on this video referencing the other videos. There's 3 of them specifically. The frequency counter video where I upgrade the Agilent and show that. The GPSDO when I initially install that and some background information there. And then also the taking the Lab Atomic for 800 when we did the 800 subscriber video, when I went past the GPSDO and onto some atomic reference, or I got an atomic reference for my lab. The important thing for that was all for stability and accuracy of time base. So the way this stuff all works is it starts with a GPSDO. Now, mine was a Samsung module that I picked up off of a auction site. And a couple of things that I looked for, and I would be interested to hear everybody else's thoughts on this, but I don't know if sine wave output for your 10 megahertz is better or if square wave output for your 10 megahertz is better. From a noise perspective, I would go with sine because it's less high-frequency content running around in the lab. But from a triggering standpoint, having the fast rising edge would be easier to find for the device that's reading it. So my GPSDO pretty much looks like this. I have it running on an 8-volt power supply. I do have the serial port hooked up, and I'm using a software program called Lady Heather to read the data stream out of the GPSDO. Now, typically what you'll find with these is they will come out of cell towers, both these and the rubidium units. If you're in the used market for one of the rubidium units, be very, very careful because some of them do not output, well, some of them output 5 megahertz, some of them output 1 megahertz, some of them output 1 pulse per second. Not all of them output 10 megahertz and run from there, which gets into some other problems. But on my unit, I got a 10 megahertz out, and I got a 1 pulse per second BNC. Now, the important part is the 1 pulse per second BNC because this gives us some integration time. In the GPSDO testing video, I showed how the frequency was being adjusted by the disciplining of the oscillator, but that means it's being yanked around. So the problem is with a reference being yanked around, your counter reference, external reference, is being yanked around too, which is going to affect the measurement up front. Now, how much does it affect the measurement up front? Well, the testing came out to be, it was moving around, but it was moving around in the microhertz. So I can't answer that question for you. It has to be, only you can answer that question in your lab for how many zeros of precision you needed. My goal was as much precision as I could get for a moderate cost. Now, if you look up some of these units online, you will find out some of these would not be considered moderate cost for some people, which is totally okay as well. These units aren't too bad. It's the rubidium units that get a little pricey. However, when you compare the cost of the rubidium unit to the cost of, say, a H-Maser, it's a moderate cost. I saw a 10 megahertz hydrogen maser that was for sale. It was $195,000, and that's US. So you can spend an obscene amount of capital on getting very precise 10 megahertz references. The nice thing about this is, especially with these GPSDOs, these get really good for not too much. I think when I picked mine up, they were about $100. I think they're at like $250 now, depending on if you can find them. Still not too bad. Now the nice part is, this is a self-updating unit, so it uses the timing signal from the GPS satellites. More satellites, more accurate. I've seen mine hooked up because I have an external antenna. It's had 12 to 15 satellites apiece, or at a time, so nice and stable. But the way the GPS satellites work is they send timing marks, and the transit delay is what the math is done on. So the satellite knows precisely what time it is, as precise as its clock can be. But they're backed up with the cesium clocks at NIST. So you have the cesium clocks that are disciplining the GPS satellites that are beaming data into my antenna for the lab, which is then disciplining my GPSDO. That would put this at stratum 1. So the cesium clocks at NIST are stratum 0. They are the definition of it is this time. We go down 1 to the GPSDOs. Now, I'm having a problem with the actual time clocks in the lab, not the references, not the 10 megahertz references, but the day clocks, the 12-hour clocks. And they're not keeping decent time. Their computers and computer clocks are pretty garbage. One of the things I'm going to be adding shortly, because I have a lot of people asking me to do a bunch of testing on some of these units, and I want to, and I have not forgotten, I want to get a better frequency counter for that. One of the newer Agilent units. If anybody has any recommendations on what I should look at for that, let me know in the description below. But I'm looking for long-term data acquisition. I want to do testing over days and weeks. And so I need to focus less on the UI and more on the data acquisition side for this particular testing, which is fine. The unit that I'm looking at is a frequency counter that has a onboard OCXO, and it'll discipline to an external reference, which I'll also do. So to get the most accuracy out of it, it's going to have pretty much all the different types of clocks then hooked up to get the best accuracy. So in the chain, we're right here. We have the antenna outside, which is beaming me data from the GPS satellites, and it's getting locked into by this device, and it's then disciplining this both 1 pulse per second out and this 10 megahertz out. And I'm monitoring it with computer software that I can record data with. And this was good. Depending on the needs of somebody's lab, this is a great way just to get started. And this could also be the stop point for some people. This is enough. It's enough precision. They don't need to worry about it. This is excellent precision over weeks, months, years. As we showed in previous testing, it's not stable. It's not awful, but it's not stable over moments, seconds, minutes, hours, because it drifts as it self-corrects. The longer these are on, too, the less that drift gets. So right in the beginning, when they turn on and they start syncing, they get dragged all over the place for a little while, and then they settle down. This is why I don't want to unplug these in the lab, and I do run the Rubidium 24/7 and the GPS-DO. Agilent uses this exact same setup in their mobile calibration trailer as the main reference for the trailer, and they do I believe it's a 2-day stabilize, so they can start doing some adjustments like within a couple of hours, but then for the really sensitive stuff, I think it's a 2-day is what they have to wait for the rubidium to settle down. So out of this 1 pulse per second out, we then have a BNC cable that comes over to the rubidium unit. For those that haven't seen the video, this is the rubidium unit for the lab. It is a FS725, and this is made by Stanford Research Systems. This is just a power enclosure. If you go on their website, you'll see a module that comes out. Actually it's about as big as a deck of cards, and that module is in here. This is also a power supply, and this is a very stable, very quiet power supply and a distribution box. I did buy the option 3 version, which put all the distribution trays in it to give me plenty to hook up. That way I didn't have to burn power in other places to keep my lab power consumption down. You can actually see right here where we are locked to the 1 pulse per second, and you can see it pulsing. That's telling me it's getting input. Once, and only once, I've had to reboot the SRS box because it lost the 1 pulse per second sync. My hunch is, because I am in North America and we do things the weird way, the rubidium unit got lost due to time change. So when we jumped forward an hour, it got all kinds of confused because its timing data got really out of whack and it didn't know what to do. So it gave up and went into holdover. So the rubidium unit gives me moments, seconds, hours, a day, maybe even a month of stability. The rubidium will wander away from 10 megahertz. It will stay stable, but it'll drift up and down, especially as the rubidium lamp ages. And that can create frequency. Well, it'll pull off your frequency. The thing with the rubidium is it's so slow, you're probably not going to notice it until you hook up a frequency counter to it, realize it's off. Even in the manual for the rubidium, they recommend calibrating it regularly, or you can hook it up to a 1 pulse per second, get an external reference for the rubidium, and that makes it ageless. So I do not have to worry about, is this 10 megahertz, because I have it synced to 1 pulse per second coming out of the GPS-DO, and then I have it, and then it's also locked to the rubidium. So the 1 pulse per second is steering the rubidium oscillator to keep it at 10 megahertz. It's not going to let it drift too far off point. Because if I didn't do that, just because of component aging and stuff like that, it might be 9.9999997, something like that. So it can drift a little bit, and there's even a alignment potentiometer on the back of the unit to bring it back to 10 megahertz, but I don't have to use that because of the syncing to the 1 pulse per second. And we will, in this video, we'll take a look at the software for the rubidium standard, and we'll take a look at some of the timing to see how well it's doing, because it's been on since that video went live and I bought it. This unit is on a UPS. It's on one of those small Liebert UPSs just to keep the power clean, keep it online, and if we ever have a brownout or anything like that, this thing stays powered up and locked. It doesn't have a problem. The GPS-DO is on the UPS as well, so I don't lose the settling time for both of the units if I have a power interruption briefly. You'll have to forgive the back end of the rubidium unit. So we have the serial cable for me to monitor it with the PC. This is the 1 pulse per second in, as you can see labeled here. Here's the frequency adjust. This turns it into a VCO, a voltage controlled oscillator. And there should be Where's the pot? Maybe it's on the front. There's a potentiometer too that you can tweak to bring it on or off frequency, although I would not. I would do it the 1 pulse per second way. I would, if I had to actually calibrate this as a standalone unit, I would probably send this one out. There's a lot that goes into making sure this is stable, and there's a lot of time. It gets real in the weeds getting one of these lined up. These cables here are to various units in the lab. We got some that go this way, and then we have some that go over this way. I have lots, as you can see, lots of 10 megahertz. I also have 4 or 5 megahertz, and I have 5 more 1 pulse per second outs. So this is taking the 1 pulse per second in, 1 PPS in from the GPSDO. I have a 50 ohm terminator on here, not because of it needing 50 ohms, but the input was running a little hot and I didn't want to burn it up. Although this is actually warm. Like these rubidium units, they do get a little toasty when they're running. So this is, this is getting a little warm. But the physics package is over here on the side. So let's see. We have one thing hooked up to the 5 megahertz because I was able to fix it. One of the reasons we have so many options here, we don't have any 1 megahertz. I don't think. No, just 5 and 10. Before everybody settled on 10 megahertz for references, some devices take 5, some devices take 1, some devices take 1 PPS. And then some just have phase lock. And I have all of these in the lab. Now, the not to chew up 10 megahertz ports, which my spectrum analyzers and my signal generator and a few other things need, because I could set the TG501 to 5 megahertz. That's what this 5 megahertz one is. This is the time mark one of the time mark generators. The other time mark generator has the high stability OCXO crystal in it, so I'm letting that run, and I'm going to kind of compare the two with each other, just doing some experiments. This allows me to fan out the 10 megahertz to the lab. Now, depending on what measurements you're doing, cable length may need to be taken into account. So at the high end, you may have to hook this all up with the same length cable, things like that, because coax cable, depending on how precise you need the phasing of the clocks and things like that, coax cable can act like a delay line, and where you could get phase differences just from having a different length of cable. So that's another thing that can be weird. I don't have any of those problems in the lab yet because I don't have any gear that's that fast, but it's just something to keep aware of and check the manuals of the gear you're using to see if that's going to be a problem. Now, outputs from this, we have plus 7 dBm into 50 ohms. Of the TTL outputs, it's 0 to 5 volts into high Z, 2.5 volts into 50 ohms, and the 1 pulse per second has I think it's a 10 microsecond delay, and it's a TTL output. So, okay, so we've gotten over to the output of the rubidium side, and we now have an ageless, stable 10 megahertz reference for the lab. Now what do we do with it? Well, first things first is we have to send it out. Sending it out could use a distribution amplifier. So what we have here is we have in and out. This is an 8-port. Obviously, I don't need this at the moment because I have the distribution amp built into the rubidium source. But I have this for when I need it again. And I did use this for the GPSDO only before I got the rubidium. The important thing here is this is actually a CCTV distribution amplifier, and it's 75 ohm because it's designed for some camera work, but it works just fine for distributing the signal. Just watch your inputs and outputs in terms of power so you don't hit any gear too hard. I did have to knock the signal down on some of the pieces of gear, even from the Stanford research unit, because it was running a little hot on the inputs. Some of the spectrum analyzers specifically, they were, if I didn't put a pad on it and an attenuator, it would have overdriven the input and probably done some bad things to the spec can. So we have some frequency counters. This was specifically what I was asked for to hook up, and actually these are going to be in some future videos. We have a Nixie tube frequency counter that we're going to work on. This one I have some plans to be the frequency counter for my 7603. So we'll go from there, but it needs to be restored first before I can throw it on the bench. This is a very inexpensive frequency counter, 100 megahertz. Runs on a crystal, nothing special. And it does not have anything on the back except for the power connector. I've been toying around, taking this apart and maybe putting a BNC on it for external reference, but I haven't gotten that far yet, and I need to see what the internal crystal is, if it's 10 megahertz or not, or if I have to work on something else. But this is very susceptible. Actually, since this is cold, this will demonstrate warm up pretty well. Okay, so this is not hooked up to a function generator. This is hooked up specifically straight to the 10 megahertz. Uh-oh. Well, I've got confidence in my 10 megahertz. I don't have confidence in my B&K. So this would be out. And this is kind of where the external references come in, because it helps the clock internally, sometimes even overriding the clock completely into... Actually, you know what? Let me warm up the Agilent because it's hooked up to the 10 megahertz. And overriding the clock completely, so it takes the inferior clock of the device, even my spectrum analyzer's inferior clock of my device, and lets it use the precision of the atomic source, the rubidium. So the nice thing is, the way you use this, let's see, turn this off, is a lot of these units, they have an external reference. Like this one even switches internal or external as to which reference you want to use, the internal clock or the external reference. And so I can take the precision of the external reference and have a self-adjusting clock. And what this does, especially for getting up a bench and getting it going, is it gives you a basis of accuracy for frequency. The basis of accuracy for frequency, especially when working on timing circuits, TG501, a couple other things, is very important. The other video I'll link in is the function generator video, where I look at the clocks on and off the rubidium. And what we found out is it tightened up the clocks quite a bit, which allowed me to use the 4000 series function generator with some of my calibration kit, because the Fluke 5200 does not actually have an external reference. It has a phase lock. The difference between the external reference and the phase lock is, regardless on what the input frequency is on this frequency counter, it wants 10 megahertz here because it's referencing the clock. On the 5200A, I need to use the function generator because I have to set the function generator frequency the same as the front panel frequency on the 5200, because it's only a phase lock, it's not a reference. That's a little bit of the difference. So, on this Nixie tube counter, this can take an external reference, I believe. It doesn't take an external reference, but you can... I thought there was a way you could compare it, like input A to input B, or something like that. I thought, maybe not, but yeah, this Itron 600, this does not have an external reference at all, so nothing to hook up. Once I set an appropriate gate time on the 5313A, the longer the gate time, the more precision the measurement. So, and as we can see, much better than the B&K, 10 megahertz. Now, it's kind of almost not fair because we have the external reference and the internal and the measured waveform from the absolute same source. So it's pretty easy to make it stable. You can tell on the frequency counter, see if it'll zoom in, if it'll let me zoom in enough. It says external ref. So that's what tells you. That's what tells me that I'm on the external reference, and I have the rubidium stability for the time base. So when you order one of these frequency counters from Agilent, especially the new ones, and even this model line, there was 3 different crystals that could come with it. It's the base crystal, which especially for this many digits is meh to no good at best. Then they have a OCXO, and then they have yet another upgrade, which is a high stability OCXO. And really, to get the stability, you have to have an external, or to get the accuracy out of this number of digits, you really need to be on an external reference or have the high stability time base. The one that I'm thinking about ordering, or the one that I want to order to do the data acquisition stuff, I want to use both. I want to have the hyper high stability time base, and I want to be on the external reference. Now, just to show what happens, because I tweaked this a little bit before I got started, if I put a gate time, so I have a gate time of 10 seconds, but if I put the gate time to 0.1 seconds, which is what it is when at boot up, at least what this is set to for the default, you'll notice we lose some digits of accuracy because the gate's going so fast. And we can even drop this down further. Gate time. And we have a very fast gate, but we lose a lot of digits of accuracy. This is one of the reasons why when I do those statistical analysis of the clocks, it takes so long, because I have to have a long gate time, and I have to do averaging of 500 to 1,000 measurements to get some of the statistics. So that's why some of that testing can take days. Okay, some of the relevant data right here is PT, which I have set to a value of 8. That's the time constant of the PLL loop. Set at 8, the PLL time, the integrator time constant on the PLL is 18.2 hours. So even though it's the GPSDO is pulling it around, this is taking quite some time to take those readings and then decide what it wants to do to adjust the phase of the rubidium, to steer the rubidium back into 10 megahertz. The time tag, or TT, is the other parameter that's important. And what that is, that's a ratio of the 1 pulse per second input to 1 pulse per second output as measured in nanoseconds. So what this is saying is, because it has a TT of 7, we are lagging 7 nanoseconds with respect to the 1 pulse per second output of the back of the 725. And the 1 pulse per second output is generated off of the 10 megahertz sine wave. So we're synced up within 7 nanoseconds of the GPSDO, which is then tying us back to the clocks at NIST. So we have that accuracy flowing through all the way till I get to my end units, or I should get to the test equipment in my lab. So here's the cable coming off of the rubidium standard going into the back of the function generator. This is the 10 megahertz reference. And a lot of the medium to higher end gear has these external reference ports on it. I'm even starting to see it on some of the entry-level gear. I really want to get a scope that has a 10 megahertz reference in it. The spectrum analyzers are on it, and to be pretty honest, some of my spectrum analyzer clocks are pretty awful, but they were made to be portable, not stationary lab high precision. They got bounced around in a truck, so they didn't put the good time bases in them. Because I have the rubidium standard in the lab, I'd like to get as much stuff as I can on it within reason. Obviously, I may run out of ports and need some amplifiers and a few other things, which is fine. But it just gives me the most accurate clock I can for a moderate cost when comparing the cost of the GPSDO plus the rubidium unit plus the external antenna that I had to put outside to a $50,000 cesium beam tube, $195,000 hydrogen maser. Moderate cost is relative. But what does this also do for calibrations and alignments? One of the things the external clock does for calibrations and alignments, because I now know I have an ageless frequency reference, I can set timing circuits and be confident that they work. The other, or I shouldn't say that they work, that they're accurate. The other thing is, with it overriding the time base in my function generator or my frequency counter, I bought the frequency counter from secondary market. It came to me. I didn't know if the clock was even calibrated or not. It was way out of cal. Using the external reference, I get to not care because I'm relying on the stability of the reference, not the stability of the internal clock of the device. So it let me use the counting function of the frequency counter with a known good clock. So I was able to scale the hurdle and get the time generators set, so I could start setting up the oscilloscopes and things like that. So it let me get around a calibration step, and I never have to worry about it as long as I'm synced to the 1 pulse per second. I never have to worry about calibrating the rubidium. It will stay 10 megahertz, and I just need to watch for it if it ever drops out of sync. As that is one of the main challenges with gear from the secondary market, regardless of what it is. I've got it. I think it works. Can I trust it? So that's one of the reasons why the alignment and calibration videos are so in-depth and things like that when I'm working on the scopes and other devices, is because the goal for my lab is I'm not looking to get it super tight to the NIST standard of the volt or the hertz or the ampere. What I'm looking for is factory specs. I want everything on the bench. I don't want anything in the lab that's a shelf queen. I want it all to function, and I want everything on the bench to, when I turn it on, I know it's in factory spec. So those are my targets. I can't say what anybody should or should not do because they're not my lab. So you guys have to make that determination for yourselves. But for me, I'm good with factory spec. So I hope that cleared up a few things when it comes to 10 megahertz references and how and why I use them in the lab and how I got from where I'm going, or where I came from and where we're going. If anybody has any questions, comments down below. I read all the comments on all the videos, and I will see everybody in the next video. As always, more is always on the way.